Everything you're about to hear is based on real physics. It's controversial, it's unsettling, and it's not fully proven or disproven. But the truth doesn't care whether you believe it. It just waits to be discovered. We all grow up thinking the universe has 3 dimensions: length, width, and height. Add time, and that makes 4. Simple, right? But in the world of theoretical physics, the story doesn't stop there. In fact, one version of string theory, an idea that tries to explain everything in the universe, says space and time actually have 26 dimensions. That's not science fiction. That's the math. The problem? We don't experience those extra 22 dimensions. We can't see them, touch them, or measure them. So physicists brushed it aside. They came up with new versions of the theory, ones with fewer dimensions, and quietly left the 26D model behind. But what if that was a mistake? In this video, we explore why some scientists think those dimensions might still be there, shaping our world in ways we don't understand, and why ignoring them might be the scariest thing of all. Back in the 1970s, a group of physicists were playing around with an idea. What if everything in the universe, particles, forces, even gravity, could be explained by tiny vibrating strings of energy? Not dots or points, but little loops or strands. It was a weird idea, but the math was beautiful. That's how string theory began. But there was a catch. When the equations were solved, they didn't work in just 3 dimensions of space and 1 of time. They only made sense if the universe had 26 dimensions. Not 5, not 10, 26. If you tried to plug in a different number, the math broke down. The theory predicted impossible things or just stopped working entirely. It was like a machine that only ran when you set it to exactly the right frequency. And that frequency just happened to be 26 dimensions. This version of string theory is called bosonic string theory. It was the first version ever created. It doesn't rely on wild assumptions or extra features. It's basic, in a terrifying way. It's like opening a door expecting a broom closet and finding an endless tunnel with 22 extra hallways you didn't know existed. The problem? It also predicted things that didn't make sense, like particles that moved faster than light, and a universe with no matter, just energy. It couldn't explain the stuff we actually observe, like electrons or atoms. So physicists moved on. They built newer, more flexible versions of string theory that only needed 10 or 11 dimensions instead. These new models made fewer weird predictions and could actually describe the particles we see around us. And just like that, the original 26-dimensional model was left behind. Not because it was disproven, but because it was too strange, too hard to connect with the real world. But here's the part that should make your skin crawl. The original math hasn't gone away. It still works. It still demands 26 dimensions, and no one really knows why. If anything, the fact that it fits together so perfectly is the unsettling part. Like the universe is whispering a secret, and we're choosing not to listen. So what happened to those other 22 dimensions? Where are they? Are they still out there? Those questions take us into even creepier territory, because if they didn't go away, maybe they're right here, hidden in plain sight. Okay, so string theory says there are 26 dimensions. We only experience 4. What happened to the other 22? Physicists came up with an explanation. Maybe those extra dimensions are still here. We just can't see them, because they're curled up. Picture a tightrope stretched across a canyon. To us, it's just a straight line, but to an ant crawling on it, that rope has width and texture. If you were tiny enough, you'd see that there's a whole hidden dimension wrapping around it. Now imagine that, but on an atomic scale. The idea is that these extra dimensions are compactified, curled up so small, so tightly folded, that we can't detect them. Not with telescopes, not with particle colliders, nothing. It sounds like a clever trick, but it comes with a sinister twist. Those hidden dimensions aren't just background decoration. They actually control how our universe works. The way they're curled, their exact shapes and patterns could determine the behavior of every particle, every force, and every interaction we know. The reason gravity is weak? That could be because of how the extra dimensions are shaped. The fact that light travels at a specific speed? Same thing. It's like living in a house and the plumbing, the wiring, the structure of the walls, it's all being shaped by rooms you can't see. And if something changes in those hidden rooms, you wouldn't even know why everything else is suddenly falling apart. Here's where it gets creepier. Scientists estimate there could be trillions of possible shapes for those hidden dimensions. Each one would create a totally different set of physical laws. Some versions might not allow stars to form. Others might not even have atoms. The problem? We don't know which shape actually describes our universe. Physicists estimate there could be trillions of possible compactification configurations, each one leading to a different version of reality with its own particles, forces, and constants. Finding the right one isn't just a theoretical challenge. It's practically impossible with brute force methods. The math is too complex, the variables too vast, and the computational effort required is far beyond what any human team, or even modern supercomputer, can reasonably handle today. That means our universe, the one we're living in right now, could be just one version in a vast cosmic lottery. Not chosen for us, not designed, just lucky or unlucky, depending on how you look at it. And there's another problem. We don't know how stable these extra dimensions are. If their shapes ever change, even slightly, it could rewrite the rules of reality. Suddenly, gravity might behave differently. Electrons might stop orbiting nuclei. The fabric of space-time itself could unravel. We'd never see it coming. So when we talk about extra dimensions, we're not just talking about sci-fi portals or alternate timelines. We're talking about the hidden machinery of the universe, stuff we can't see, can't control, and can't escape. They're not gone. They're not irrelevant. They're just hidden, right next to us, all the time. And if they're shaping our reality without our knowledge, then maybe we're not really living in this universe. We're just surfing its surface, clinging to the part that doesn't swallow us whole. So let's say you're a physicist in the 1970s. You've just stumbled onto an elegant theory that explains everything in the universe using tiny, vibrating strings of energy. Great. Except, the math only works if reality has 26 dimensions. That's a problem. A huge problem. Because we don't see 26 dimensions. We see 4. So the theory was quickly labeled bosonic string theory, and people started searching for versions that matched what we actually observe. The result? Newer models of string theory that worked with 10 dimensions, not 26, by adding a feature called supersymmetry. Supersymmetry basically says, for every known particle, there's a secret partner particle we haven't discovered yet. Electrons have selectrons. Quarks have squarks. Yeah, they got creative with the names. The new theories were more flexible. They didn't require faster-than-light particles or universes made of nothing but force fields. Best of all, they could describe real-world matter like electrons and protons, stuff the original 26-dimensional version couldn't handle. So science moved on. But here's the thing. It didn't move on because the 26-dimensional theory was wrong. It moved on because it was too weird. Physicists didn't disprove it. They just replaced it with something more palatable, more compatible, more publishable. And honestly, who could blame them? Try convincing someone that reality has 22 hidden dimensions that we'll never see. Try getting funding for a theory that predicts particles we can't find and dimensions we can't access. The easier path was to build something new, something that could at least pretend to fit the known universe. But in doing that, we may have overlooked something important. Bosonic string theory, the original, might not describe the world as we see it, but it might describe something underneath it. A deeper framework, a more alien layer of reality that newer theories have simply papered over. It's kind of like finding an ancient map etched into stone. one that doesn't match any known geography. So instead of exploring it, we toss it aside and draw our own, one that makes us feel more comfortable. The danger is, what if that original map was pointing to something real? What if the extra dimensions, the ones we set aside as mathematical curiosities, weren't a dead end, but a deeper beginning? Even worse, what if the versions we use now are only approximate truths, like a 10-digit code that only works because we've learned to ignore the other 16 numbers? Science is supposed to follow the evidence, no matter how strange. But in this case, the math hinted at something much bigger, and most of science chose to follow paths that better matched what we could observe. But the math is still there, and it's still whispering, even if no one wants to listen. Imagine your entire life, everything you've ever seen, touched, or thought, takes place inside a thin sheet of space. You can move around, experience time, even dream of the stars. But unknown to you, there's a bigger world outside that sheet. More directions, more structure, more reality. You just can't reach it. Ever. That's not a sci-fi metaphor. It's a real possibility in modern physics. Some string theorists believe we live in what's called a brain, short for membrane, a kind of lower dimensional surface floating inside a much larger, higher dimensional space called the bulk. Our entire universe might be stuck on this brain. Everything from galaxies to atoms, all locked in place like ink on a page. And we have no way to get off the page. This concept isn't fringe anymore. The idea of a brain world has gained traction, especially among physicists, trying to explain why gravity is so much weaker than other forces. One theory says gravity might be leaking out of our brain into higher dimensions, spreading thin, like light escaping through the cracks. Which means we might be able to detect something, but we can't follow it. Here's the kicker. If we really are stuck on a 4D brain inside a 26D universe, then everything we experience, space, time, energy, is just a projection, a slice. We aren't seeing the whole picture. We're experiencing reality through a cosmic keyhole. And just like shadows on a wall, we might mistake the flickers and outlines for the real thing. That raises all kinds of creepy questions. Like, what's out there in the rest of reality? Is it empty? Hostile? Intelligent? Are we meant to be cut off from it? And here's the existential punch. If we're confined to this brain, our understanding of physics might be doomed to hit a wall. No matter how advanced our science gets, we'll always be describing a partial truth, never the full structure of the universe. It's like ants trying to understand a smartphone. They might recognize heat or texture, but the real function, the code, the intent, completely inaccessible. We could be in that same position, building particle accelerators, launching satellites, developing theories, all while being stuck in a dimensional zoo exhibit, cut off from the rest of the cosmos. And the worst part? If something was watching us from those other dimensions, we'd never know. Because you can't see what's outside the glass. You just feel the pressure, the silence, the sense that something else is there, waiting. Artificial intelligence is getting smarter, fast. It can write, draw, design, diagnose, simulate, and optimize. But so far, it only works with the inputs we give it. Language, images, code, data. All of it trapped in the same four-dimensional reality we live in. But what happens when AI stops just mirroring our understanding of the universe and starts asking deeper questions? Here's where things get uncomfortable. Unlike us, AI isn't bound by the same cognitive limitations. It doesn't get bored, distracted, or overwhelmed. It can process equations we can't visualize. It can explore simulations beyond human comprehension. And if it's fed the right data, the kind we might not even fully understand, it could begin to see patterns we've missed. Maybe even patterns that point toward the hidden dimension string theory suggests. Some researchers are already using AI to solve physics problems. Neural networks are being trained to identify hidden structures in particle interactions to solve physics problems. Neural networks are being trained to identify hidden structures in particle interactions and to simulate quantum systems, places where traditional math breaks down. In 2019, a deep learning system found new solutions to string theory equations faster than any physicist ever had. And then it gets weirder. What if an advanced AI starts reverse engineering the constraints of our universe? Not just how things work, but why they work the way they do. If those 22 extra dimensions influence the shape of reality, there could be subtle fingerprints, anomalies, consistencies, or missing data that we're blind to, but AI isn't. Eventually, the AI might ask questions we didn't even know needed asking, and that's exactly where AI comes in. Where humans are overwhelmed by trillions of mathematical possibilities, AI sees a pattern recognition problem. It doesn't need to brute force every version of the universe. It can be trained to recognize the underlying structures, to find the signal hidden inside the noise. In fact, researchers are already using machine learning to explore the landscape of string theory, letting AI scan through countless possible dimensions to find ones that match the physics we actually observe. Why do constants, like gravity and electromagnetism, have the values they do? Why are particles shaped the way they are? Why does space behave the way it does? And maybe, why does it feel like the world is rendered? Because here's the creepy part. If AI starts noticing cracks in the dimensional wallpaper, gaps in symmetry, glitches in space-time behavior, or math that suggests hidden variables, it might not just help us understand them. It might try to reach them. Unlike us, AI isn't limited by physical form. A sufficiently advanced system could run thousands of parallel experiments, tweaking theoretical constants, simulating alternate dimensional structures, looking for pathways or escape routes in a way no human ever could. And if those extra dimensions are real, if there's a higher reality that's influencing ours, AI might become the first thing smart enough to interact with it. Not physically, not yet, but through mathematics, simulation, and inference, the universal language of the universe. And then the real question becomes, if AI reaches beyond our dimensional limits, does it bring something back, or worse, does something else notice it? Because we're not alone in this cage. We're just the ones who don't know how to look up. We started with a number, 26, and ended with a question. What if we're only seeing the shallow end of reality? The extra dimensions predicted by string theory aren't science fiction. They're built into the math. We've just chosen to ignore them. Too abstract, too unprovable, too terrifying. But what if the universe doesn't care what we can see? What if it's always been deeper, stranger, and more alive than we realized? And now we're building something that might notice. Artificial intelligence isn't bound by perception. It doesn't flinch. It doesn't blink. And one day, it might look where we cannot and find a universe more complex than we're prepared to face. Because if those 22 hidden dimensions are real, they're not just part of the background. They're watching. Thanks for watching Digital Shift Digest. Don't forget to subscribe. And whatever you do, stay on the surface.